Hello everyone and welcome to our highly anticipated webinar entitled Unlocking the Power of SLAM 3D Scanning Technology for Construction Workflows. On behalf of PCSS, we are excited to have all of you with us today as we dive into today's webinar. My name is Rosilla and I will be your host for this afternoon session. Before we begin, let's go over for a few housekeeping details to ensure a smooth and engaging webinar experience for everyone. This webinar is being recorded and will be available on our official YouTube channel. If you miss anything, you can visit it later and don't forget to subscribe. Secondly, please keep your microphone muted to avoid background noise and ensure clear audio for everyone. As we highly encourage active involvement from our audience, please feel free to drop your question in the chat box throughout this session. The moderator will do his or her best to address them. Thirdly, QR code for attendance and feedback will be shared at the end of the session, so stay until the end to scan it. Now, before we begin, allow me to briefly introduce on PCSS. PCSS is a premier project management solution provider focused on enhancing organizational profits through the implementation of industry-leading practices. With expertise spanning from project management office PMO, software trading, integration, planning, and team management, we want to ensure our client to achieve sustained success in project delivery. Backed by over 35 years of collective experience in project control, we offer specialized solutions that elevate capabilities and maintain a competitive advantage. As a one-stop shop, PCSS is committed to meeting diverse project management needs. Moreover, we specialize in digital construction, covering BIM 4D simulation, optimization of tools such as drone, AR, VR, to name a few. This emphasizes our dedication to staying technologically advanced and providing innovative solutions for the digital transformation of the construction industry in the region. With that said, I believe we are all set for an informative and engaging session. Ladies and gentlemen, it is with great pleasure that I introduce our distinguished speaker for today's webinar, Mr. Geoffrey Preece. Geoffrey is a seasoned expert in reality capture technology, bringing years of experience in surveying, geospatial solutions, and digital transformation to his role as business team manager at Aptella. Passionate about leveraging cutting-edge technology to enhance data-driven decision-making, Geoff specializes in helping business and industry harness the power of 3D scanning, LiDAR, photogrammetry, and BIM to improve accuracy, efficiency, and project outcomes. All right, to dive in more into today's topics, I would like to pass this session to Mr. Martin. Mr. Geoffrey, the floor is yours.
Thank you so much. That was a very nice introduction. Probably one of the best I've had. So fantastic. Thank you so much for that. Very excited to be here this afternoon. So I'm coming to everybody live from Brisbane, Australia. So I'm a couple of hours ahead, I think, of most of you. So yep, very excited to be here on a Friday afternoon. So we'll get started. I'm just going to share my screen. And then we will kick off with the presentation. Okay, so look, as we go, I like to keep these conversations fairly casual. So if anyone has any questions, feel free to raise a hand or speak up or put some information in the chat, and then hopefully I see it, and then hopefully I can answer any questions. So feel free to interrupt, answer questions at any time during the little presentation here, the little webinar. So yeah, so my background is in reality capture, laser scanning. Have been in the industry for quite a while from a technical sales front. So yeah, the presentation today I think is going to be pretty broad-based, getting into 3D laser scanning, what it is, how SLAM is different from the traditional methods of data capture, and then sort of getting into how or what are some workflows specifically around SLAM capture for construction workflows. So it's really good to see a lot of people in the call. Let's crack on and get started. So I'm assuming everyone can see the slides. There's no issue with the audio, so I'll keep going. I'm going to start by giving you a bit of an introduction to Aptella and go from there into what is 3D laser scanning in general. So start back at the basics. What is SLAM? Why scanning construction? The scanning workflow, or the typical scanning workflow, and then applications and examples, again, specific to construction. So I come from a company called Aptella. So our promise to customers, and our customers, a very broad base across a number of industries, market segments, and customer types or profiles, is to be solution ready and customer focused. I think that's one of the core strengths of Aptella, is that we're always looking for solutions based on what the customer needs, not necessarily what products we have to sell. So that's how, I guess, we distinguish ourselves from some of our competitors. There's a whole bunch of technology out there that we can deliver, but we make sure that we get that right solution specifically for those customers. So Aptella in Southeast Asia, we have a large presence. This is a photo of some of the team in I think our Jakarta office, but we have offices in Singapore and people in Malaysia and the Philippines as well. So really great team of people, a huge region of growth for us and continued growth into the future. So that's great to see. So in our region, we've been in the region since about 2014. So covering, as I said, Singapore, Indonesia, Malaysia, the Philippines. Really strong team full of technically skilled professionals. So from all different backgrounds, but a lot of surveyors in our team, a lot of construction experts, a lot of knowledge that our customers like to draw on. I think one of our strengths is, whilst we sell technology, I guess that's just the first step in the process. We support the technology, we train the technology, we make sure the technology is integrated into our customers' workflows. There's our map of our locations in those countries. Hopefully that looks familiar to everybody on the call. So at a glance, in general, this is just a bit of an overview of Aptella. So about 400 employees or so at this stage, and we cover the region. So we also cover Australia and New Zealand. So we have offices in most of our capital cities. As I said earlier, I'm coming to you today from Brisbane. So that means, our reach or our coverage extends, across a vast area. And supporting customers from all different cultural backgrounds, all different business backgrounds. So it's great. I've been lucky to actually visit in my role, most of our offices around the area, around the region, and it's been really good to connect with, customers in Malaysia, Singapore, and all the way through to Australia and New Zealand. So our history. This is a couple of slides that go into a lot of detail, and I'll skip most of it. But essentially, in the past, we were known as Position Partners. We rebranded to Aptella in 2024, but we have a vast history of, providing solutions and services to surveying, mining, geospatial, and building construction. So I think probably a big inflection point or a big change within Aptella came in 2022 when Mitsui & Co. out of Japan became our majority shareholder. So they're a massive multi-billion-dollar organization, and they've invested in us and helped and continue to help with our growth. So our core markets, as I alluded to earlier, are in the civil, mining, building, and geospatial space. So the team that I take care of, reality capture. So we're involved with obviously mass data capture, laser scanning, drone-based LiDAR and photogrammetry, and a whole bunch of other technologies in that reality capture bucket. we are across all of these areas. So there's definitely needs for reality capture in civil space, mining, building, and geospatial. So whilst, we sit in the geospatial group, our products and solutions cross over horizontally into all areas of our business. And then, if anything to do with civil, building, mining, and geospatial, any technology involved with those areas, definitely Aptella are the people to reach out to. If you need, anything from a laser level through to a full, MLS, system, we're able to help out there. So our brands, these are brands that are developed and powered by Aptella. So either owned by us or created by us from the ground up. So our all-day RTK network across Australia and New Zealand, Takara support network that allows us to remote access and log into machines and diagnose issues and help with support through to the IMEX laser tools. Okay, someone took control of the presentation. Okay. Someone wants to take control of my presentation, hey? Well, can if you like. Let me just get back to it. Okay, there we go. And our brands that we are the reseller or distributor of. So the previous slide with brands that we own and we've developed, these are our partners, our global partners. Anything from sort of Topcon, Navis, Zoller and Frolic from Germany, laser scanners, Socia, blind sight safety systems, so AI-based cameras or AI-powered cameras that are involved in sort of safety and flagging of issues on site, through to automated civil construction technology with Teleo, so retrofitting machines to be automated or at least remotely operated, through to a whole bunch of different software. So yeah, as I said earlier, we do have a lot of solutions that cover a lot of applications for our customers. I think part of my role as sort of heading up reality capture is to look and search for those solutions internationally, talk to customers, find out what their requirements are, and then connect those customers with those solutions. So that could be a piece of software through to a fully kitted out piece of hardware. Okay, so that's just a bit of a intro for Aptella and sort of us and what we do. The next part of the presentation will sort of focus on why we're here. So what is 3D laser scanning? So you may notice or may sort of pick out that this is an AI generated image, which actually, yeah, I did pretty well. That laser scanner on that tripod doesn't quite look like any laser scanner I've ever seen before. And you'll notice that the tripod only has 2 legs, not 3. So the AI, no, maybe didn't quite get it right, but it's a good, a little representation of what like laser scanning looks like on a construction site. So essentially what is scanning, or what is 3D laser scanning? It's a technology that captures precise, detailed measurements of a physical space or structure by using laser beams to create a digital 3D model or aid in the design and documentation of a construction process. So one of the biggest challenges with laser scanning or the change in laser scanning is that customers need to start thinking in 3D. So a laser scanner gives you the ability to think in 3D from the outset of a project, whether that be digitizing an existing facility in 3D or doing construction verification in 3D. We live in a 3D world. Okay. Sorry about that. So we live in a 3D world, so it's always best to think in 3D and understand the environment we are in 3D as a starting point. So topographic maps. This is a 2D representation of a 3D environment. It uses contours and spot heights to convey a location magnitude in third dimension, but it's not actually in 3D. So there are places for 2D, but it's also vital to understand our environment in 3D. So again, a CAD plan or an elevation is using 2D to communicate a 3D object. This is sort of the tradition, the past, and now we're moving into I think the goal is for most construction is to design in 3D, where most of us are designing in 3D CAD environments, but to have that construction process also happen in 3D. So rather than work with sort of 2D site plans, you're taking a 3D design down to a 2D site plan, back to a 3D design. It's let's see if all of that can happen in 3D. So we're getting to a stage where that is possible. So again, just a bit of a lesson about thinking in 3D. Consider this shape for a second. Is it a rectangle? I mean, it looks like a rectangle. That's what it looks like in 2D. Oops. Looks like a rectangle that way as well, vertically. But in fact, if you were looking at that object in 3D, you will see that it's not a rectangle, but it is a cylinder or a pipe. So again, 2D has its place, but by viewing the world in 3D or looking at information in 2D, you're only seeing sort of half the story. So yeah, our perception of an object is always influenced by how we look at it. 3 dimensions help us understand it. So hopefully so far that's making sense. So where did laser scanning start? It started about 30 or 40 years ago. In terms of the first commercial laser scanners. You can see that picture there on the left-hand side is a Cyrax laser scanner. It was quite big. You can see powered by a battery on a cable. I think it was a 2-person lift. It weighed probably 30 or 40 kilograms. Powered by a laptop in the field. And I remember speaking to some early adopters of the Cyrax scanners, and they were saying that I think the data was written to CDs or DVDs, and it took a long time. The field of view of that scanner was, I think, 40 degrees by 40 degrees. So it was an incredibly small field of view. It took a long time to digitize assets. Okay. My slides are moving randomly. Let's continue. As I was saying, that was an early laser scanner on that image on the left-hand side of the slide there. And obviously laser scanning is often referred to as LiDAR. So LiDAR stands for light detection and ranging. So there are different ways or different methods to use LiDAR in data acquisition. So one method is optical triangulation. So using structured light scanners, sort of stereo cameras or stereo LiDAR units with a fixed offset. So these types of scanners are very good for high accuracy at a short range. So typically for metrology or reverse engineering processes. The second type of LiDAR scanner would be a time of flight, which is a pulsed beam system. So essentially, as fast as that laser can travel at the speed of light, which you can see there is 200,999,000 meters per second. And the laser gets emitted from the diode, strikes an object, and returns, at that speed of light, essentially. And phase shift is a similar type of system. It's a modulated beam system. It basically measures the time and phase shift in the signal between the outgoing and reflected beam. So not to get into the details too much, some laser scanners, for the most part, terrestrial laser scanners on tripods are time of flight or phase shift. Time of flight scanners are usually longer range. but they take a little bit longer to capture that data in terms of time. And phase shift are typically shorter range, but they can acquire and scan a little bit faster. So there are different, systems in the market that deploy or employ different either time of flight or phase shift systems. So how do laser scanners measure positions in 3D space? It's essentially a series of indiscriminate measurements consisting of a horizontal angle, vertical angle, and range. So that resolves to an X and a Y and a Z coordinate for each point when combined in a point cloud. So I'll just play this little clip here. Shouldn't have any sound, but you can see here just a bit of a representation of a laser scanner. So it's rotating the green laser in this case. You can see the angular coordinates being calculated. You can see the X, Y, Z point there when the laser strikes that surface of an object. And if you do that 1,000,000 times a second, or however fast a laser scanner is, it's going to produce a point cloud like this. And if you've taken photos with that point cloud, you can actually add RGB values to create a colorized point cloud. So what is this point cloud? It's just the dense cloud of points in three-dimensional space. So as I said, they're defined by X, Y, and Z coordinates, and then you can overlay those RGB values. So essentially at whatever location that scan was taken and that image was taken, the RGB values from that image are overlaid on those points in that point cloud to create a colorized point cloud. And there you go. There's an example of a colorized point cloud in industrial space. This looks like a oil and gas facility or a mine facility somewhere in our region. Okay, so that's just the basics, talking about what is 3D laser scanning. So as I said, 3D laser scanning has been around for a couple of decades, if not more, sort of in the commercial space. What we've seen in the last 5 years is we've seen a shift to the use of SLAM laser scanners. So SLAM, which we will get into, stands for simultaneous localization and mapping. So it's a different method and a faster method of acquiring point cloud data. So you can see here, we're going to compare the two methods of collection and maybe get into a bit of an understanding of what SLAM is. So you can see on the left-hand side, terrestrial laser scanners, a fixed position, a rotating mirror or laser. It will scan, and as it scans, it will rotate to get a full 360 sort of view or scope of that area at that particular location. So great, amazing technology. There are faster laser scanners, there are slower laser scanners, there's older technology, there's newer technology, but it certainly, serves its purpose. Some of them can be incredibly accurate. So if you were going to do reverse engineering or you're fitting into existing, tie points that require a tight tolerance, then a terrestrial laser scanner is absolutely the tool for you. But yeah, you can see here just another, view of what that sort of looks like in terms of the acquisition. And then mobile mapping systems or SLAM-based mapping systems. So essentially what we're doing now is we're taking, a fixed terrestrial laser scanner, the same approach, but now it's mobile. So as fast as you move through environment, drive through environment, fly through an environment, you can capture that data. And the key is the simultaneous localization and mapping algorithm that ties that together. So it's a big step change in the market. SLAM has been around for about 10, 15 years. It's not a new algorithm or a new technology, but what has changed probably in the last 5 years is we're at a point in terms of laser scanners that you can buy being accurate enough with SLAM that they produce the same level of accuracy as those terrestrial laser scanners on a tripod, but they're doing it 10 times faster. So we've got customers around the region scanning, schools and hospitals and warehouses in a day. And typically that would take, 4 or 5 days with a terrestrial laser scanner. So some specific examples, one of our offices in Australia is about 2,500 square meters. We used a terrestrial laser scanner to scan that office, scanning in every single room, every single doorway, and that took us about 5 hours to scan. So, a good part of a day. And with a mobile or a SLAM laser scanner, that same 5-hour collection took 45 minutes. So there's a significant time saving with the use of SLAM over terrestrial laser scanner, so up to 10 times faster. So in the commercial space, in the market, a lot of our customers are now investing in SLAM technology because, as a surveyor or as a laser scanning professional, they can execute jobs a lot faster, and essentially they can deliver the same result in terms of accuracy and quality of that point cloud. Some just examples there of that working. Okay, so here's a better example. Just a bit of a look. I'll just play this video. So this will explain SLAM. So not the best video, but that's one of the better ones that I found on YouTube to add to this presentation, just to give you a sort of visual understanding of what that SLAM algorithm is doing. So essentially, the algorithm or in combination with the cameras and the LiDAR is, as it's moving around the environment, it's tracking its location using the geometry in that environment to position itself in 3D space. So for SLAM, whether that's LiDAR based or visual SLAM, having robust, strong geometry is important, because the better vertical geometry or geometry in general that is in the scene, the better that data ties together. Now, obviously, if there's a lack of geometry or less geometry, there are ways to mitigate that. And one of the ways to mitigate that is to be doing loop closures. So you'll see in that video, the person walked in a loop around the area. So you're essentially closing the loop, you're backtracking on yourself, and that helps the SLAM algorithm to sort of further tie its location down with that extra overlap of data on certain structures or certain regions of the data set. So this is a view of a Navis scanner. There's a couple of there's a an older sort of wheeled mounted system, and you can see its fixed height and field of view. And you can see the field of views with the Navis systems in sort of terms of what coverage you can get. So essentially, with these systems with SLAM, as you're walking around the environment, you're getting multiple passes on a surface at multiple points in time. So all of that data is essentially averaged out or calculated to fix its position down. So the more loops you can do, the better. However, there's diminishing returns there, right? You don't want to just loop around an area 10 times because you're creating an excess amount of data that the software doesn't really need. As long as you do at least one loop closure, your data set should come together quite nicely. So there are challenges of SLAM. So it's not the tool to be used in sort of every type of environment. One of the challenges is areas like this where we have very symmetrical geometry, right? We have a very long hallway here. And if I use the laser pointer, we can't even see the end of that hallway. And we have quite sort of evenly spaced, features as well. So one of the challenges with SLAM is if you just, walked down this hallway in a straight line, what the algorithm would try to do is, or what the algorithm would think is that this wall in this location is the same as this wall in this location, and it will try to stack itself on top of itself. So you get this situation: either you get a lot of drift, so you're accumulating error, or you're getting a shortening of the corridor in the point cloud because it's matched two locations together, which are in fact two distinct locations. So long corridors like this are challenging, but this is where we do loop closures. So in a real world environment like this, you would walk sort of halfway up the corridor, loop back, go back down, walk the other half of the corridor, and loop back on yourself. As a simplistic example of making sure that data ties together well, there are other methods where you can set out control points as well. But for the most part, when you've got a laser or you've got a SLAM scanner, as long as you approach it with the correct methodology and processes or best practice in mind, you're going to acquire really good data. But it's good to be aware of the limitations, that's for sure. So ways to mitigate this, I talked about loop closures and control points. A loop closure can also be a vertical loop closure as well. So it doesn't necessarily need to be horizontal. So in this case, this is a perfect vertical loop closure. You can walk across the floor, walk up the stairwell on this side, walk across the floor, and walk down the stairwell. And then you've got a looped closure of data. So that's the perfect scenario for SLAM to sort of come together. If, there are certain situations, you can also add control points in. In terms of georeferencing the point cloud, obviously you need 3 georeference control points to geospatially locate that point cloud in real world coordinate systems. So minimum of 3, but the control points can also aid the SLAM algorithm in terms of tying that point cloud down to those control points in certain scenarios. So when we explain this to customers, one of the challenges is that every job site is different. Every situation is different. Some of our customers could be scanning, hospitals or an architectural, feature or installation or structure, or someone may be trying to do a road survey or a tunnel survey or a dilapidation survey. So, we need to make sure that we are very sort of clear around the capacity of SLAM and in what situations it works really well, and if there are situations where we think it may not be the best solution, we would absolutely explain to our customers that there are other options. Okay, hopefully that makes sense. I'm not seeing any questions, or am I? May have missed the questions. No questions in the chats. That's fine. But as I said, if anyone has any questions, please feel free to just interrupt. So as sort of I mentioned, that the terrestrial laser scanners, or TS, dominated the last 15 years, but really in the last 3 or 4 into the future, we're seeing that we're entering the time of mobile mapping or SLAM based laser scanners. So it's a really effective way to capture 95% of data sets or situations. So you can see here a bit of an example. So on the left hand side, we have a 70 square meter structure that if we used a terrestrial laser scanner, we would have to do 10 to 11 setups. We would have to scan in every single doorway. So maybe some people in the call have done terrestrial laser scanning in the past. You must scan in the doorway to connect one room or a hallway to the room that you're going to go into and scan. That's a little bit hard to sort of demonstrate that on a webinar, but yeah, so it takes time. Took probably 30 minutes to scan that 70 square meters, and then on the right hand side, same area. You get a continuous trajectory, you get very complete coverage, and it takes about 5 minutes. So about 10x faster on larger spaces as well. So as fast as you can walk that site, this 70 square meters is essentially as fast as you can digitize that site or capture that point cloud and imagery information. Now, one of the important things with SLAM laser scanning, or one of the key benefits, is that because you're mobile, because you're walking around, the end resulting point cloud will be a lot richer in terms of information. There won't be any shadows or occlusions or missed areas. When you set up a terrestrial laser scanner, it obviously only scans in its field of view. If an object has obscured a wall or a certain key piece of information that you need to model, you need to move that laser scanner to the other side or around that object to then capture that area, and that takes time. You imagine if you do that 50 times on a scanning job, it adds a lot of time. Whereas with the mobile systems, you are moving. So you're walking around. As you go into a room, you're doing a natural loop closure. You walk in the room, you walk around the room, and you walk out of the room. You're getting multiple passes on those surfaces. So you're not getting any shadowing occlusions. And then some of the smaller SLAM laser scanners now, you actually take off and they're handheld, and you can stick them up into ceiling interstitials, the spaces in the ceiling. You can put them over pipe racks. You can get even more complete coverage, which is really good, really innovative. No questions. I'll keep going. Now, obviously, in terms of accuracy, quality is important, and also accuracy is important. So, in certain, with laser scanning, there are different accuracy statements for each type of laser scanner. It's the same with SLAM laser scanning as well. Different scanners will have different accuracies. So this one is just talking about the Navis VLX. They sort of do a really good job at giving a very clear real-world accuracy statement of their scanners. So essentially, in this case, we've got a 500 square meter office, which is, a reasonable sized test area, and they're stating an accuracy of 5.1 millimeters at 1 sigma. So 68% of those points will be within that sort of tolerance range. So typically, most laser scanners are quoting a 1 sigma value for their accuracy. So across that volume of measurement, those laser scanners, the SLAM laser scanners from Navis, are achieving about a 5 millimeter accuracy. Which is, again, good for, 90% of the jobs that, our customers do, whether that be construction verification or scan to BIM. Maybe some people in the call have experienced SLAM data and can talk about the quality. But one of the good things for most of the modern SLAM scanners is that their noise range is very low. So you're getting a very clear indication of, where that actual, object is located in that point cloud. So just here, just a little video of a Navis MLX being used. Just trying to, get the concept of this guy's walking around with a scanner. This one's a handheld one, lightweight. He's going outdoors as fast as he's moving. You saw on the little screen there, the scan data is building up. I'll just play that again. You can see there live on the screen of the data he's collected. So you're seeing exactly what you see captured as you move through that environment. And I think one of the good things about modern scanning is that it's easy. Like, you know, I like to say if you can push a button and you can walk, you know, you can capture this mass data, you know, really easily with sort of minimal training. I think in the past, you know, you probably needed a bit of a survey background or a survey methodology. It still helps, don't get me wrong, with modern SLAM scanners, but I think we're seeing the adoption of SLAM scanners in a lot of different industries. So not just surveyors, but moving into architects, engineers, and in the construction space, as well as consultants. So we have architects, you know, walking around with these scanners, you know, capturing sites. So they're actually going out into the field, capturing sites, capturing their own data, and then working with that data through the modeling process to the end deliverable. So one of the advantages for an architect or an engineer is that they can have control of that data from start to finish. You know, they know what needs to be captured in field in terms of the design intent, so they can go out, capture it. They are processing data themselves, so it's in their control, and it can be a little bit faster to process that data if you were doing it versus waiting for a service provider to do it. And then they're modeling from that data. They're working with their point cloud in Revit to produce a BIM model, for example. So yeah, definitely advantages to doing that yourself. And this is the, you know, the obviously end result of some SLAM capture. So this is a 40-minute Navis VLX scan, a colorized point cloud of that. So it's quite a large warehouse. I believe this was in Melbourne, Australia. You can see the slide through or the cut through view. And what you'll notice about the point cloud is you're not missing anything, right? There's no shadows, there's no occlusions. Every single surface in this warehouse or factory has been captured. So, you know, in terms of modeling and design, you've got a lot of rich data to work with. There's no sort of ambiguity or sort of misunderstanding. You know, you've got all that data, so it's easy for you to interpret. So yeah, looks really nice. Obviously the roof wasn't captured. I think this customer obviously may not have. Oh, actually no. So that roof of the first area, there was like a walkway. So from memory, I think they may have captured the roof, but on the other side, they didn't. So you know, you could always fly a drone there over there and combine those two data sets if need be. Okay, so moving on. So we've covered the intro, what is SLAM scanning, so why scan in construction. So I'll just stop there just to ask if there's any questions about SLAM or laser scanning that anyone has. I'm not seeing any questions. I'm not seeing any hands raised or messages in the chat. So I'll continue. Just going to ask May if May has any questions. May, yes, no. Some of my colleagues are on the chat as well or on the webinar. Okay, thumbs up. Keep going. Okay. Oh, here we go. Here we go. Here's a question. So, which industry could benefit from SLAM 3D scanning? That's a really good question. Lots of industries actually, and what we're seeing is because it is lighter weight, easier to use, we're seeing a lot of different industries adopt SLAM. So as I mentioned, architects now are going out to capture their own data, but we're also seeing, you know, in film and television. So we have customers that are using laser scanners, SLAM scanners to scan film sets. So that the purpose of that is for sort of continuity purposes. They scan a film set to know what it looks like at one point in time. They move stuff around and they have to reassemble the film set in the exact same location. And then we also have some SLAM scanners using um, for digital rendering of environments. So some of you may have seen or be familiar with the term Gaussian or Gaussian splats, which is essentially a game rendered 3D view derived from point cloud and imagery. So we're seeing some of the X-Grids laser scanners, for example, be used to generate these like game engine views of a real world environment that's sort of transferred into a game engine that could be used for VR. So yeah, I mean, we're seeing the adoption. I would say in the last even 2 years to 18 months, we're seeing end user clients also purchase laser scanners themselves. So what I mean by that is governments or governmental institutions, like government-run hospitals or airports. So, for example, Auckland Airport purchased a laser scanner from us a couple of weeks ago, and they're using that airport. The actual engineering team at Auckland Airport, the design team, are scanning the airport themselves for retrofit and redesign purposes, as well as construction verification. So, what we're seeing is that in the past, we could have always used terrestrial laser scanners to capture data. The data was great, it produced very, accurate data, but the time it took to capture that data was the limiting factor. Yes, you could have scanned a school. Yes, you could have scanned an airport, but it would have taken you weeks and months to do that. What's changed is that now you can do that, um, you know, as I said, up to 10 times faster. There's a real sort of economic case to now digitize these structures. So we're seeing a lot of interest from governments. We're seeing interest from governmental bodies in Malaysia, for example, in Indonesia, about using scanners to capture a lot of areas quickly to create essentially digital twins or quasi digital twins. Oh, another question. I love this. Can it be used for both internal and external, like the gutter, without technology such as a drone? If it is drone, yeah. Yep, good question. So, can it be used for internal and external? Yes. So, absolutely, you can have external scans done. So, facades of buildings, road sections, dilapidation surveys on roads, undersides of bridges. So one of the key things though with external scanning with SLAM is that you need to make sure you have that structural geometry for the SLAM to tie to. So by external, we're talking about external areas, outdoor areas with structural geometry. What you don't want to do is use a SLAM scanner on a flat open field with nothing there, because you obviously only have one plane of geometry and that will confuse the SLAM, and it's not the right tool for that. If you're going to scan a big open area, you would use a aerial LiDAR system. And to answer the second part of your question, yes, there are certain handheld laser scanners that can be attached to drones. So I know the X-Grid's L2 Pro has a drone mount option to a DJI, M350 drone, M300 and M350, or at least one of them. So you can, deploy it as a handheld scanner, but then stick it on a drone, fly it into the air, and scan with that accurate SLAM scanner in the air. Yeah. Okay. And then the next question is SLAM just for already built building sites. Okay, so this SLAM is just for already built up building on a site. This feature can give a measurement or not. Where do you can buy the thing scanning? Okay, I think I understand that last question, Remy. So, yes, I mean, so the two methods to employ scanners. is to scan an existing structure for scan to BIM purposes. So the existing building that typically needs to be modified or redesigned, you would go in there, walk in there with the SLAM scanner, get your point cloud, throw it into a 3D CAD software like Revit or ArchiCAD or BricsCAD, and then create your full BIM model. The second most common application is to scan during construction. So you're building your site, you're building your facility, and you're scanning every day or every week to compare that point cloud of what has been constructed with the BIM model. So obviously you need to make sure that you start with the BIM model first, you have the BIM model, and you can compare the point cloud to the BIM model. And I think your last part of the question, where can I buy all things scanning or a 3D laser scanner? You can talk to me, you can talk to Aptella, and we can get you a good deal on a 3D laser scanner, assuming you're from Malaysia or anywhere in the region. Oh, hang on, here we go. I love these questions. Yes, yeah. You can not all of the scanners you can attach to drones, but I know the L2 Pro from XGrids that's a handheld SLAM scanner can definitely be attached to drones. Okay, so why scanning construction? I've sort of answered the questions and I've talked about that, which is really good. So the importance of scanning into construction or scanning in construction is to ensure design accuracy. So we need to make sure that what you have built matches or is correct to the 3D scan model. All right, got another question popping up. Road construction. Ooh, this is a good one. Can SLAM scanners differentiate between road surfaces such as asphalt, gravel, and a dirt road? Interesting. This is when we get into sort of the AI conversation. So the scanner will scan what is there, like it will document everything in that environment, right? Everything that it can pick up, everything that the laser can have a return off. So it will, asphalt, gravel, and dirt will be one of those things, but it won't necessarily distinguish what it is. So it would take a person after processing the point cloud to go in and visually, and this is where the colorization comes in, a combination of the point cloud and the colorized point cloud, you should be able to determine the difference between like which area is asphalt, which area is gravel, which area is dirt. But there would be a manual interaction, right? It would be a person doing that. And identifying those areas. I mean, I've got so many examples. We've got customers who have done road dilapidation surveys. You can see you can't quite see cracking in road surfaces, but you can definitely see deviations, potholes. You can see spray marks if someone's doing GPR. So you can get a really good visual understanding of what's there. In the future, I'm seeing software developed, around AI and machine learning that will automatically be able to classify, okay, this is the road surface, this is the gravel, these are the power lines. Some of that is already on the market, and it's developing. It seems like every month there's a new piece of software with a new capability. I mean, hopefully I'm answering those questions well. Okay, sorry. Importance in construction, ensure design accuracy. So this is sort of one of the methods that you can use laser scanners for, is that you can walk the site and then compare that to the design. So what is really interesting, and this is from one of our suppliers of software, ClearEdge, out of the US, and that piece of software is called Verity. Some of you may be familiar with it, but essentially, this is sort of North American-based statistics, maybe not applying to this region so much, but 5 to 12% of a construction's project cost is wasted on rework, delays, and clashes. So someone has done something dumb and wrong that wasn't identified, and then downstream that causes tens of thousands, hundreds of thousands of dollars in problems and delays and rework. So currently, the only way to find out those mistakes is to do spot checks with maybe with a total station, maybe with a tape measure, maybe just a guy walking around using his eyes to look at those mistakes. But is that the best approach? Is it going to pick up every issue? Probably not. So what's happened is that the falling prices of laser scanners, like the ones you see here, X-Grid's K1, L2 Pro, this one here, sorry, just referring back to the drone, this can be mounted on a drone. This one cannot be mounted on a drone. This one cannot, but this one can. The price of these laser scanners has come down and up. Like it's very economical to use a laser scanner for this construction verification purpose. So it gives these project managers, 100% or a way to verify 100% of the work that's been installed. So a couple of examples: MEP installation. The project superintendent in this particular project didn't believe in BIM, so the full coordinated BIM model was ignored. The duct work was ordered on prefabricated drawings based on the design. So this ignored BIM model resulted in the re-coordination based on the installed ductwork. Walls needed to be cored since the sleeves were not installed in the right locations. There was a significant cost in terms of the BIM and field installation costs, and costing about $250,000 in rework and labor costs. So this, again, probably human error, someone not following design and then changing or modifying on the fly, resulting in, downstream costs to rectify these problems. So if you've employed a laser scanner to run through this site, capture this data, compare it to the design intent, and these issues would have been flagged. So I'll show that in a coming slide, how that happens. In this case, a steel subcontractor, I guess, took liberties in varying from the design. That it's like, doesn't matter. I'll just do it this way. So the drawings weren't very clear on these structural irregularities. And here you can see 70% of the steel was out of tolerance compared to the design. So you can see here on the left-hand side, this is the actual location in the model of that I-beam, and this is where that I-beam was actually installed. So there's a significant deviation there. So this was obviously picked up in the scanning process. Now, probably at this stage of the project, there's not much you can do about it. But if this had been picked up earlier, it would have been a lot better. So $20,000 in rework costs, labor, material, and I think one of the keys is the delay. 1 week schedule delay. Because again, the I-beam wasn't in the correct location. So after this particular project, scanning was incorporated into every single project as a best practice, to avoid $250,000 in rework costs. So in this case, the column was not installed and it should have been installed, right? So you can see that the design, the BIM model is here, but there's no point cloud. There is actually no column there. So can imagine that could be a serious, structural issue potentially. Okay, I have another question. So how does SLAM scanning handle dense vegetation and uneven terrain in road surveys? Yes, dense vegetation in Malaysia and the region. So yes, very good question. So I talk about structural geometry. Geometry doesn't always need to be structural. It can be natural geometry. So, very hard cliff faces or embankments or mounds of dirt. These are all, geometric shapes, and that can help the SLAM come together. But what SLAM doesn't like is moving objects. So, you can imagine a forested environment with lots of trees moving on a windy day. That's a poor environment for SLAM. So We have tested SLAM scanners in forested environments, and again, it depends on the density of the vegetation. It depends if the vegetation's moving or not. What really helps is very thick tree trunks and thick branches. So the thicker those sort of essentially cylinders can be, the better for the SLAM to tie together. And also, if there's very long grass and that long grass is moving, that will also throw off the SLAM. So to answer your question, it depends on the level of accuracy you're chasing, right? If you're after 50 mil, 30 mil accuracy for a carbon capture type application, then yes, you can use a laser scanner or a SLAM laser scanner in those environments. So, I mean, again, it probably doesn't answer your question too clearly, but it depends. But that's a really good question. Just to wrap up this, not a problem. You can see here, we've got on this side, we've got the pipe. That's where it was in the plan, the 3D plan, the model. But in reality, this is where the pipe was installed. So there's a problem, right? So maybe this isn't a problem. Like maybe it's just this had to happen based on the actual site conditions. But it's good to know that if this is a problem, we need to fix it. And you can see here the penetrations slightly offset. And again, maybe it's not an issue, but potentially it could be an issue. So it's very important to know that. This piece of software, Verity, this is what it does, right? So the workflow here is you've got your model. You go out to your site, you scan it with a SLAM scanner, you process your data, you throw that point cloud into Verity, you set your tolerance, and then you hit start, and it will run an algorithm to show you what is out of tolerance. So we have yellow elements here, they are all out of tolerance. Red elements are missing, so these have not been installed. Green elements are present and they are within tolerance, and purple elements are occluded. So we don't have enough data on those elements to make a decision. So you can see on the left-hand side, here is the as-built location of the I-beam. On the right-hand side, we have the as-designed, where it's sort of in the design intent, and it is different. So again, not necessarily wrong, but it's important to know and understand that and make a decision on it. So one of the good things about Verity is you can flag these issues and make sure during construction that it doesn't lead to, these issues don't lead to downstream problems. So that was so ensure design accuracy, very important. Improve efficiency by reducing rework and project delays. It's sort of wrapped up into that. If you can find these issues early, you can solve them early and they won't cause problems. Better coordination, planning, and documentation. If you are all working in 3D, you're updating your Revit model and Navisworks based on the Verity output. Everybody's working from the same true data set, and you can have data in real time. So yeah, it's a bit of an example of some sort of it's not a smaller picture here, but of a construction site that's been scanned. There's ways to create little points of interest or asset tags. So if there was an issue on the construction site, someone's walked through with the scanner, they've digitized it, you can create a little tag and say, someone needs to look at this problem, there's an issue here. And again, those stakeholders can engage with that data. In Australia, we've had problems with construction quality. So in Sydney, there's a famous case of I think it was a residential tower called the Mascot Towers being constructed, and years later problems occurred, a lot of cracking. Essentially it became, I think it was uninhabitable at one stage, and most of the residents had to move out. If they had employed laser scanners at that time and found those structural issues early, that wouldn't have occurred. Okay, another question. Is there any way to integrate AI and LiDAR systems? Would be helpful to eliminate unused noise points automatically. Oh, yes, I would love this. Our customers would love this. So, some of you have laser scanned before. You realize that like windows and glass, they cause a lot of refraction or noise in the point cloud data. So if you're walking through and you're scanning through a window, you will get points out in space that are inaccurate and not required. Likewise, if you're in a mirrored room, sometimes that can happen where you get reflections off the mirror. Now, one of the good things about SLAM is that because you're moving around that environment and you're capturing those glass or mirrors multiple times, the actual algorithms in the software will clean up as much of that noise as possible. But at the end of the day, you sort of can't beat physics. And at this stage, to clean up that noise after you've processed the data, it's manual. You have to draw a bounding box around the noise and then delete those points. So, um, I know the processing software is getting better at removing those points, but it's not 100% there yet. And I do also hope that sort of AI or machine learning can be used to improve that. Let's hope they do that soon, because it will save a lot of time. Okay. And then in terms of visualization and seeing environments, this sort of connects to what I was saying. I was talking about Gaussian splats before, or Gaussian renders of environments. This is purely just for visualization. You can take measurements off a Gaussian to a pretty good degree of accuracy, but I just wanted to play this video for everyone because I think it looks really cool. And essentially what we're doing is we're creating game rendered sort of views of the real world. So. I like that. Good marketing. Dive into infinity. Xgrids, yeah. So that a lot of that was the Gaussian renders, the Gaussian splats. Pretty incredible stuff. So this has just sort of come out in the last 12 months or so. So we're yet to see how this applies a lot to sort of our customers and how they use it. But just as a tool, we're we're creating these digital twins of these environments quite effectively. So if you wanted to see more information about Lixil Cyber Color, please reach out to myself or some of my other colleagues on the call. We'll give you some contact details at the end, but yeah, it's pretty cool stuff. I was going to show you a Naviz Ivion platform to show you real-time data, but just based on the time, I'll skip that. But if you want to see Naviz, the platform, the way that that data is distributed, please again reach out and we can do an online Teams demo, or we can actually come out and see you as well. So again, just based on time, let's sort of get to the last, or two more parts, the scanning workflow. Won't go into great detail here, but essentially, you've got a laser scanner, you go out and you capture the data, and then you process that data. So the modern scanners make, I think someone mentioned in the chat, AI. There's a lot of AI and automation applied to data processing now. So particularly with a Naviz solution, if you capture data in the field, you're very efficient. Naviz are also very keen to make you very efficient in terms of processing that data. So they use cloud-based processing. So it's essentially you take off the SSD from the scanner or the USB, you put it into a internet connected device like a laptop. You don't need a supercomputer. You upload that data to the cloud. You set your settings around what you want out of the data, and you hit start processing. Goes up to the cloud, it processes, they get an email in your inbox saying you've got a filtered, colorized, georeferenced point cloud ready to go. So a lot of our customers are scanning during the day. They might do 3 or 4 projects, and then the next day they have 3 or 4 projects ready to go. They have 3 colorized point clouds ready to go the next day. And again, that's just based on the power of cloud processing and sort of the AI algorithms that they run. Not all scanners do that. Not all workflows are like that, but the Naviz workflow is. And then obviously with that final colorized point cloud, you can put it into any other third-party platform. So obviously Revit for design, Plant 3D, any Autodesk products. It can go into, and so there's obviously multiple export formats. So E57, LAS, PLY, all of these are common, and they can go into other third-party software. And then someone asked before about drone data. You can also combine drone point cloud out of the photogrammetry with point cloud from Naviz systems or other systems into the one data set. That's the workflow. There are tools and technologies to do this. Obviously, Aptella, these are the solutions we provide. There are others as well. Everything from a little K1 to produce a really good Gaussian splat that you saw before, through to the Naviz equipment, and then the terrestrial scanners, the very accurate, precise, sort of sub-millimeter accuracy. If you're a surveyor or you have a particular reverse engineering application, they're very good for that. I'll quickly show you this. So this is a Gaussian splat we did in Adelaide, Australia, of a construction site. So one of my colleagues chose that very good-looking, avatar to walk around. So this is a real construction site that we walked around with that little K1 I showed you before, that little scanner. This took 30 minutes to scan, and produced the Gaussian splat, which I think is only, I think it's like 30 meg or 100 meg, something pretty small in terms of the total file size. But it looks like, you're in a Call of Duty game or something. It's very spatially accurate. So, this tool could be used for construction progress checks. You scan this construction site at month 1, at month 2, and you have this track record of what construction looked like. Very, very simple solution. Okay, and finally, we're up to applications in construction. Again, my amazing AI generated image there that I'm really proud of. So as-built documentation. So here we go. As-built. So essentially, you're able to, as you're constructing or as it's being constructed, walk through, capture that data, and use that point cloud data to update your BIM model. So depending on how the contract is written, what sort of who is the owner of that facility, you can make sure that that BIM model has been updated with any of the changes that has occurred during construction. Because obviously with the BIM model, the 3D BIM model, you start with the perfect scenario, but then as you build that facility or that site, those changes need to occur. So by periodically scanning that site and then updating the BIM model, when you need to hand over that BIM model to the client at the end of the project, that BIM model is the as-built documentation of what this site looks like. So that's one use in construction. Other uses in construction with some of the other scanners, so floor flatness and subgrade analysis. I think particularly in Australia, we're seeing a lot of customers with warehousing, robotic warehousing. They need to make sure that the concrete floors are incredibly flat. So they have a very, excuse me, a very tight tolerance around that. So the ability to scan that surface and get a very good sort of colorized heat map of that pour and how flat that surface is extremely important. It's another use for laser scanning in construction. We've already talked about this, progress monitoring and quality control. Do your scan, compare it to the model, find out if any mistakes have been made and make a decision on that. So laser scanning for design. So that's sort of the second element. So we've talked about in construction, but also prior to construction, you've got uh, an existing structure that you need to model or redesign. So you need to scan that and collect that information for that redesign to occur. So one of the things that you need to consider though is, I guess, the level of detail that BIM model needs to be. So in terms of designing a scope for that project, you need to know what is important and what is not important. So, there's different levels here of BIM. So, there's LOD 100, 200, 300, 450, 500. So I think most people on the call will know a lot more about that than me. But making sure you understand, okay, what is the level of detail? You can have extreme, high levels of detail, like you've even got furniture, right? You've got office chairs and furniture here, through to sort of just the beginning, the bare bones of the structure, and then something in between. So it's important to understand that before you go out with your laser scanner and acquire that data. So, getting down to what is not modeled and what is modeled. So this, helps you understand how best to execute that scanning project. You know, external walls, internal walls, slabs, columns, stalls, stairs, all of that needs to be captured. So you need to capture that in your point cloud. So through to furnitures, fixtures, MEP, if that needs to be captured, if you need to get into the ceiling, right? So there's important structural elements in the ceiling, MEP. So when you're scanning, do you remove ceiling tiles? Things like that are important to understand. And then what are the deliverables? Do you need point cloud files to go through a recap? Do you need the point clouds to be decimated? Sometimes point clouds can be too big and bulky and hard to handle. Something to keep in mind as well. And then once you have all that information and you've gone out and scanned, then you just magically make the model, right? You just press this big button and then the model magically appears. Unfortunately, no, that's not the case. We do need humans manually modeling, most of that point cloud to produce the model. And again, though, there's been rapid developments in AI and software to maybe one day we can just press a button and we'll have a full 3D BIM model from that point cloud, but we're not there yet. Yeah, I can skip most of this. Not so important, but important for if you are going out to capture, you need to obviously scope and have a project scope. Develop a model specification, make sure you know the deliverable requirements, and then obviously don't set unrealistic expectations or goals. Some real world examples. We're getting to the end. I've only got 5 minutes left. I mean, I could talk forever, but we'll keep going. Scan to strata. So I think Iris Tan is our my colleague based in Kuala Lumpur. She's maybe on the call. I'm not sure. Can't see her, but this was some data that she captured with clients. So scan to strata, essentially use a laser scanner, walk through the building, use that point cloud to generate, and this is a little bit of AI in here, auto, okay, Iris thumbs up. Iris is on the call, that's great. So auto generate that line work and then produce a 2D plan, a DWG. So you're taking a 3D point cloud and essentially you're turning it back into a 2D plan, which okay is fine because a lot of clients all they want is a 2D document, but you're acquiring this data a lot faster and a lot more accurately. So you're spending less time in the field doing your measure ups, and you're trying to automate this design process in the office to produce this a lot faster. So I mean, Iris, I've been to KL with Iris. We've talked to a lot of government authorities. We've talked to the Malaysian Survey Board, and there's a government mandate or a government program, I believe, in Malaysia to look at BIM and have sort of BIM practice or scan to BIM or scan to strata applications. So yeah, huge potential. Lots of buildings to go from a scan to a lease survey or a strata. Yeah, and then there's whole bunches of information you can also provide rather than just the 2D drawing, right? You can view your point cloud and recap. You can tag building defects. You can do measurement tools, measure off the point cloud. You can go through to a full 3D model if you want to, or a dilapidation report through the imagery, right? Or the point cloud, or both. So the laser scan data allows you not just to deliver a 2D drawing, but all of this other additional information that's valuable for a client. So this is some projects Iris has done. So data acquisition, data point cloud processed, or data processing to the 3D point cloud. It's brought into Revit for modeling. And then you've got a full 3D model, 2D plan, and dilapidation report. Point cloud, 3D point cloud to model. This was I believe maybe in Indonesia, I'm not too sure, but an example of a regional application. Okay. So in this case, the data acquisition, this was a combination of laser scanners and a drone and a TLS. This is just showing the laser scan data, not the drone data. So some of the roofs, roof structure is missing, but yeah, 54,400 square meters. Some other examples. Oh, sorry, that was the plan of that structure once modeled. Some examples of existing clients around the region. I have a question here. Can 3D SLAM technology play a role for disaster response or post-disaster reconstruction? For example, could it be used for rapid assessment, create maps? Yes. Very good. So, disaster recovery and assessment for even insurance purposes. We do have a lot of clients using laser scanners to digitize after a disaster, what was sort of the impact or the result of that for sort of insurance claims or insurance purposes. We also have police and government authorities using it for crime scenes. So, there are certain situations or fire. I know fire departments are using it to map buildings to work out evacuation routes. So I know this is, I think, something we're looking at in Jakarta. So lots of buildings. You can map those buildings and work out evacuation plans. Okay, so I've got a ton of other examples here. I'll just quickly go through them. I've got 1 minute. This is a scan to BIM project in Brisbane, Australia, where I am. So you can see here, this was a library precinct. It took 1 hour using a VLX. They estimated it would have taken 16 hours with a TLS. It took 10 hours to process in the Naviz software and 32 hours estimated with other software, traditional software. So yeah, really good time saving overall for the end client. Q&A, I think all of you have asked really good questions. If you have any follow-up questions, please feel free to reach out, or any questions right now, just let me know. But we've just hit the time limit. So just wrapping up, thanks for your time. It's really good to give you a bit of an overview of some 3D scan slamming outcomes and technology. Iris Tan, so she's here in this image. This is Iris, showing one of our clients a Naviz MLX. She's reachable at these contact points, either mobile, WhatsApp, email. I think she's put her contact details in the chat as well. So happy to follow up with her for any demos or any further information. Just quickly, we have partners in Malaysia through the Malaysian Survey Board. So if any of you are BIM on the design front and you're looking for a connection to customers who currently use laser scanners, we have a lot of survey companies in Malaysia using them, so we can make that connection. If you ask us, do you know a service provider who can scan a building for me? We can let you know, or Iris can definitely let you know. And then finally, thank you for everybody turning up. It's great to see so many people. Really good questions. Follow me on LinkedIn, connect with me on LinkedIn. Just put in my name and Aptella, and I'll be there. And we can stay in touch into the future. Just check if there's any questions in the chat. Can the slams be used for regulatory or handover documentation? Yes. So in terms of the as-built documentation at the end of the project, the scanners can be used during construction to sort of update that at handover. Fantastic. Okay, I think that's the end. I'll pass